Before I dive into this, ever since I escaped from the prison of administration in 2018, I've had the honor of teaching a plant disease epidemiology class at WSU, and I use cherry powdery mildew as a disease to help teach certain components of plant disease epidemiology. And I started to use the same approach with industry talks last year, and they were pretty there are no standing ovations, but let's just say they were pretty well received compared to my canned talks of the previous 35 years. So I'm going to use that approach again today and then talk a little bit about fungicide resistance and how to deal with it. Over the years, I've had plenty of support for my research program, the Ag Research Center at WSU, the Tree Fruit Commission, the Oregon Sweet Cherry Commission, the Specialty Crop Block Grant Program. Incidentally, I only received one specialty crop block grant, and I was never able to even get a pre-proposal through after the first one. The reason why is I gave them money back. So we didn't spend all the money, and that's, you're not supposed to do that. The Commission on Pesticide Registration, and then two really great employees I had later in my career, Claudia Probst, you probably remember her, and Prashant Swami. He did a lot of the work on the fungicide resistance. As we dive into this, a little bit of background about the powdery mildews in general. They're very unique fungi, pathogenic fungi, and part of their uniqueness is they're not nearly as dependent on water as other groups of fungal plant pathogens. And part of the reason for that, these asexual spores up here that are called conidia, they carry their own water, rather as opposed to, say, a conidium of the fungus that causes apple scab. It needs a film of free water when it lands on a leaf. Powdery mildew, conidium or asexual spore does not. Then in the case of cherry mildew, we have a functional sexual stage, and those are called chasmothecia or cleistothecia. Again, it's the sexual stage, and they're spherical, very melanized when they're mature, and they have dichotomously branched appendages, as you can see down here. And these are, right here, these are appendages of the Podospora cerassi, which is the cherry mildew. And then inside each chasmothecium is a bag called an ascus, and the asexual or the sexual spores are born there. In our case, the chasmothecia are how the critter gets through the winter. So they contain the ascospores, which initiate the epidemic, and once the epidemic is rolling, then it's the asexual spores that serve to spread and intensify it. When you have powdery mildew on a leaf surface, this is what it looks like. It superficially grows on the leaf surface, sends up vertical conidiophores, and produces a spore about every 24 hours. And if you look at these, the oldest spore is always the terminal spore. And after about 24 hours, it'll break off, blow in the wind, and then the conidiophore will produce another spore. But this is the phase that you actually see in the orchard, and this is the phase that really allows things to get out of hand if it isn't managed. Again, the chasmothecia, this is what they look like on the leaf on the left. They're just brown. You can actually see them with the naked eye, but, well, I could see them at 35 with the naked eye. At 70, not so much, but I can see the brown shade. And again, the higher magnification on the right, in general, they're spherical with dichotomously branched appendages. And on the photo on the far right here, that's a chasmothecium of the pathogen that we're talking about here. And you can see it's opening. It's in the midst of spore release. It cracks open when it gets wet. The ascus pops out a short distance, and you can see the ascospores inside the ascus. So this is the only part of the powdery mildew disease cycle that requires free water. And it doesn't matter if that water comes from a cloud or comes from a pipe. But this is what this ascospore release is what initiates the epidemic. This is the disease cycle, and I got the Dr. Beers treatment here too at the bottom. The thing's dropping off the slide, but whatever. Again, survives the winter. Up here is Chasmathecia. That's where we are right now. If you had a mildew problem in the previous growing season, this is how it's surviving in the winter. In the spring, you need free water. Again, either in the form of precipitation or irrigation, and that has to occur in general between the time the buds open until about pit hardening. In the studies we did in previous years, we found that the Chasmathecia that survived the winter generally had degraded by the middle of May, which made them functionally useless unless there was a precipitation or irrigation event up to that point. Once the ascospore release occurs, it causes what we call a primary infection. Again, the ascospores will blow up to the leaves, germinate, and start to produce the asexual or conidial phase. And again, when you see the white mildew on the leaves, that's what you're seeing. So the primary infection are ascospores, secondary or conidia, and this can cycle throughout the growing season on foliage. And where we really run into problems if we have a severe infestation on foliage before harvest. It's important to remember that the inoculum that can devastate a fruit crop is actually produced on the foliage. Then as we proceed through the growing season, you'll start to see the Chasmathecia forming on the leaves, and again, it's just preparing itself for winter. This stage right here, they'll stay on the leaf and stay anchored to the leaf until late summer or early fall, and if we have a rain event, it will serve to loosen up the Chasmathecia, and they can be splashed or blown by the wind onto the cherry tree. And where they actually survive the winter are in bark fissures on the main trunk and on the main scaffold limbs. So it's very, very important to understand that phase of the life cycle. So if you look at, try to think of this disease over time, and what happened last year and years prior matters this year. And let's just say, for example, we have 3 growing seasons, and we're with differing levels of mildew, and we're coming into growing season 1 with this much overwintered inoculum. If we don't manage the disease, the overwintered inoculum will be higher the next season, and if we don't manage it that season, it's going to be even higher going into the 3rd season. So it's really important to be able to think beyond a single growing season here. What happened last year matters. If you had a lot of mildew last season, the chances of you having mildew this year are far increased as opposed to if there was no mildew last year. This is a polycyclic model, meaning it cycles many times through the growing season, and that's the secondary phase, the circle I pointed out in the disease cycle slide. But the disease progress, where you plot disease intensity versus time, it's an S curve. And obviously with a population curve like this, it's better to deal with the management part in here, because the further along and the higher you get, the more tragic the outcome is. And if you're trying to manage this disease in the stationary phase, I would consider that revenge spraying. It's best to deal with it earlier in the season. Now, this is where we try to relate this to money, and this comes out of my epidemiology class. But we have a general equation for a polycyclic plant pathogen. It's just Y equals X0 times E, which is a constant raised to the power of R and T. Y is the amount of disease at time T. X0 is the initial inoculum. T is time. E is the constant. And if you look at this mathematically, what we ideally would like to do here is be able to multiply by 0 somewhere over here. If you multiply by 0 over here, this is going to also be 0. The next best thing is to try to keep the numbers as small as possible. So again, y over on the right there, y is the money at time t. This is just the same as the equation for compound interest. X0 is the initial investment, and R is the equivalent of the interest rate. So money can also apply to polycyclic diseases. If you look at these models, there are 3 ways we can reduce Y, which is the amount of disease at any time in the epidemic. One way is to reduce the overwintered inoculum. This is easier said than done. Another is to reduce the rate of infection. And again, if you look at the curve on the right, where R is the largest is where the line is nearly vertical. But what we're trying to do is slow the R in the equation for the polycyclic model, or reduce the duration of the epidemic. Another way to look at this is maybe shift the epidemic in time. And this is actually useful with some diseases. But again, looking at the disease progress curve and X0, which is the overwintered inoculum, last season matters. If you had a bad mildew outbreak the previous growing season, the chances are that X0 is going to be higher than if you had not had an issue the following season. And again, back to this, that's what's going on. We start at 1 year. If it goes unmanaged, the next year the inoculum potential is higher, and then if it goes unmanaged the third or second season, then the inoculum potential is even higher from there. So when we're applying fungicides, and we apply fungicides until we're blue in the face for cherry mildew, what we're trying to do is to reduce the rate of disease increase. And if you look at this, at the graph here, there's some bars at the top, and the foliage bar is when the foliage can become infected relative to harvest, and the foliage is susceptible all the way up to that time. The red bar is the period of fruit susceptibility. And this is the last 2 weeks before harvest. It's right before harvest when they're susceptible. And what we want to do is keep that disease progress curve as low as possible until we get through that point. So we try to eliminate the overwintered inoculum. Some years we've been able to do that with lime sulfur, but other years we were not able to do it. And when it did work, we had to treat each tree in the orchard with a handgun at about 400 gallons per acre. So when I look back at that, all I can hear is the sound of a cash register related to labor costs. And it didn't work every year. But what we were trying to do is eliminate the inoculum. In epidemiological theory, again, looking at disease progress, again, the amount of disease here, time here, and let's just imagine we're in one growing season. The A line, or purple line, is if we do nothing. Okay, you can see the disease starts earlier. If we only reduce the amount of overwintered inoculum, disease reaches the same level eventually, but it's the onset is delayed. And this could be really important if you consider that window of fruit susceptibility. C is if we just reduce the rate of disease increase, okay, R, and we do that through fungicide applications or making the orchard environment less conducive to powdery mildew. Whereas D is if you are successful in doing both. So again, B, it's hard to get the effect. C's, if you have good fungicides that there's no resistance to, pretty consistent, but if you can do both, it's even better. So decrease initial inoculum, the best way to do that is good disease management the previous season with the fungicide program and some other things that I'll talk about in a minute. Prevention of sexual reproduction. Again, the chasmathecia are formed after harvest in general, and we found over the years that if we applied 1 or 2% petroleum oil after harvest, 2 applications, 1 2 weeks after harvest, 1 4 weeks after harvest, we were able to really reduce the amount of Chasmathecia on the foliage. The problem was we had to go to an incredibly high spray gallonage to get the effect. So somebody needs to go back and look at this at lower spray gallonages. And again, the reduction of overwintered inoculum, or X0, it is iffy. Like I said, with us, our trials, it had been consistently inconsistent. So, but again, if you control the disease well in growing season A, you won't have as many Chasmathecia had you not controlled the disease well, and that translates into inoculum potential for the next season. Ways to reduce the rate of disease increase: make the orchard less conducive for powdery mildew, pruning, mowing, and weed management. And this is an important one: sucker removal. Remove the suckers as soon as you see them, because the foliage on them is extremely succulent and let's say nitrogenous, very susceptible to powdery mildew, and it's where a lot of early season inoculum can be produced. And again, a lot of inoculum before harvest elevates the chance of losing the fruit to mildew. Keep disease levels low with effective fungicide programs. Now, this is easier said than done, given some of our challenges. So I actually stopped doing efficacy studies on cherries back about 2014, at least doing them in the orchard. And the reason why was we could no longer afford to do them, given the cost of labor, et cetera, et cetera. So I haven't done, that was the first thing that affected my fungicide evaluation program. The second thing was 5 years in administration. So I don't have a lot of efficacy data to share here, but as we talk about fungicides, resistance is a big problem, and if you need information on fungicide resistance, this website is very, very informative. It's called the FRAC site, Fungicide Resistance Action Committee. Just about anything you want to know about fungicide resistance, the extent, the causes, theories about it, you can find there. Okay. One thing that's important about fungicide programs is you need to know what you're putting on and in the sequence in which you're putting it on. If you look at the fungicide label, that information is available on most labels. And again, the Fungicide Resistance Action Committee gives these fungicides a number, which is called their FRAC number, and that's based on the fungicide's site of action. And if you're putting together a fungicide program, say for the upcoming season, it's important to know those FRAC numbers because you don't want to overuse or misuse any individual FRAC number. Okay, you hear the term mode of action and you hear the term site of action. And we use them interchangeable, but they're really not the same thing. And what you're looking at on the fungicide label for the number is the actual site of action. But before we get to that, let's go over mode of action. Okay, sulfur, the mode of action, it inhibits spore germination. DMI fungicides, group 3s, such as Raleigh, Procure, et cetera, inhibit membrane synthesis. The group 7s inhibit respiration. The 11s inhibit respiration. And I'll zero in on those two groups in a second here. The group 13s inhibit the infection process, and mineral oil or petroleum oil disrupts cell walls and interferes with host contact. Okay, mode and site of action. Again, we talked about the group in 7s and 11s in the previous slide. They do share a common mode of action. They both inhibit respiration, but they share different sites of action. That is, they inhibit the fungus at different biochemical pathways. So I can skip ahead there and there. And the group 11s and group fungicide and group 7 fungicides inhibit respiration. That automatically implies something going on with the mitochondria. And what they do is inhibit electron transport at different biochemical sites. So if you get resistance to group 7, you're not going to also get resistance to group 11. Before the fungicide resistance survey that I'm going to talk about in a second here. If you look at the synthetic fungicides we had before we found out what we found out, these are the days of wine and roses. I remember when we started with mildew, we only had sulfur. So 30 years later, we had all these products. We did a resistance survey in 2021, sampled over 100 different orchards. About 50% of the isolates were there was resistance to group 3, which is right here, about 50% group 11, and far fewer, only 2 orchards worth, group 7. The resistance was prevalent, but somewhat variable. The group 7 resistance was very rare. So that means we need to be real careful with this group 7 group because we know they're still useful. We found no discernible geographic patterns in the real fly in the ointment, as we have evidence for there being spatial variability in this at any point in time, and also temporal patterns. What you might have in the orchard early season may be different than what's there late season. Just to show you how complicated and fun this became, the resistance information from Howard Flat, we looked at 8 different orchards, and you can see we found a lot of group 11 resistant, actually in 4 orchards. In orchard 5, we actually found group 3 and group 11, and then the other 3, we found none. But think about that. You have resistance to group 11 and group 3 in orchard number 5. That's 2 sites of action that's probably not going to be overly effective in that orchard. So that's what gives us the after slide. And again, this is very complicated because there's space and time. This would be a perfect research project for someone, is to further develop the understanding of the temporal and spatial factors. These are the groups remaining, the 7s, U13, 13, U6, and U8. And again, but in any specific orchard, like for example at Howard Flat, and they're spatially close together, but like for example, one orchard had no resistance, and 100 yards down the road there was resistance to 2 different classes. So it's really hard to come up with anything real definitive. And again, assume that the compounds that we have remaining, they're high risk. The other thing with the group 11s, it's particularly problematic. There's cross resistance in the group, meaning if you get resistance to one of the active ingredients in that frat group, there's resistance to the other active ingredients. So you need to know what's in something when you're putting it in your spray program. And some of the premix fungicides, like for example, Luna Sensation 11 plus 7 is in the premix formulation. No resistance to 7, no widespread resistance to 7, but we did find widespread resistance to 11. What I'm getting at here is one of the things that we loved about premixes, that we thought that it gave us built-in resistance management. But if you didn't know you had resistance, if you're using Luna Sensation, you didn't know you had the resistance to 11, what you're really doing there, if you don't throw another fungicide in the tank, you're actually starting to promote resistance development to group 7. So it's really important to know what you're putting on. Again, the summary, 3 and 11 resistance is common, 7 very rare, no discernible geographic patterns, and definite spatial and temporal patterns. The spatial pattern, I'll just briefly mention it. We looked at it in one orchard in Richland. We did a transect through the orchard and sampled at different points along the transect, and we only found resistance at one point. So there's obviously spatial variability in any given orchard at any specific time. So I'll talk a bit about the canker survey. We did this in 23 and 24, largely I think because Frank was getting inundated with cherry cankers, and some of them, it was obvious that they weren't fungal. So we did a survey Myself, Tiana, Ashley Thompson, and Garrett Bishop, we did this in 2023. I won't go into the song and dance about how we did it, but our conclusions were cankers and dieback are widespread and prevalent. 5 known cherry wood pathogens. The bacterial canker in 2023 was the worst I'd seen in my 38 years here. It was definitely the worst situation with bacterial canker I've ever seen. I actually saw bacterial canker in some coral champagne that made me so happy it brought tears to my eyes. I really had never seen anything like that. But we also found 4 fungal pathogens. Most common fungal pathogen was leucostoma. We used to call this cytospora. Same pathogen that we found in our 1990 surveys as being prevalent. We found another one, Callispheria. This is the primary fungal canker pathogen of cherries in California. We found Callispheria in both Oregon and Washington. Eutypa lata, which is also a wood pathogen of wine grapes. And in 24, we found 2 orchards with Batriosphaera. The Callispheria and Eutypa were not found here in the late 80 or early 90 surveys. The northernmost Callispheria that we found in Washington was on the south exposure of Snipes Mountain. Only found it in one other location by the mouth of the Walla Walla River. Callispheria is far more prevalent in Oregon. It is the primary fungal canker of cherries in Hood River and the Dalles. And again, the Batriosphaera, we found 1 case of it in Benton County and 1 in Klickitat. They're very variable in morphology, whether in tangential or cross-section. Mixed infections are relatively common. The first case of Callispheria that we found in Washington, the one by the Walla Walla River, was we had been in there during harvest, and I found Cytospora leucostoma throughout the orchard, but there was 1 tree that had leucostoma but looked a little bit on the odd side. So I flagged it, went back in the fall, and then I found Callispheria on the same tree also. These are easy to identify in the fall if you find the fungal fruiting bodies. You can see them with a hand lens, but again, more likely to find these in the fall. And we isolated over 40 different types of fungi from these cankers, some of which we identified, some we haven't yet. And someday someone needs to take those and do pathogenicity tests with them. So that's the upshot of the cherry canker information. That Amanita mushroom really has nothing to do with cherry cankers, but it is a fungus. So, thank you.